Howdy. 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 Wait about one more minute. Okay, I'm going to get started. Hello, everyone. Hope you're doing well. What? Hang on a second. I don't know why my document camera isn't showing. Class, I'm going to be right back because I have to restart my streaming software. All right, I'm back. So today we are going to talk about something called rotational kinetic energy. So the idea of rotational kinetic energy is somewhat artificial. So what do I mean by rotational kinetic energy? Well, there is so-called translational kinetic energy, which is the energy of a thing moving from point A to point B, okay? But something can also be rotating, which is if its orientation is changing, okay? So this would be rotational kinetic energy. So you can have rotational kinetic energy without translational kinetic energy. You can have translational kinetic energy without rotational kinetic energy. Or you can have both. Okay? Now the formula for both of them is 1/2 mv squared, but it, you know, it's typically written in a different form when we're talking about rotational kinetic energy. So let me show you. We're going to derive the equation for it. Let's imagine you have a block of mass m, and it has it's moving in a circle. Okay, so it's going around a circle. That circle has a radius r, and it's moving in that circle with a velocity v. Okay, so the kinetic energy associated with that is just going to be 1/2 mv squared. Okay, like I said, it's not really any different from translational kinetic energy. It's just a useful separation of the kinetic energy into two terms. Okay, so as this thing travels, eventually it's going to end up right here, for example. All right, and it's going to have moved by an angle theta around the circle. Okay, and then there's a certain arc length, which I'll call s, which is the distance traveled. So we learned that equation that s equals theta r. So the arc length around a circle is equal to the angle subtended by that arc times the radius of the circle. Okay, so we already used this equation. So if I take the derivative of both sides, I get ds dt equals d theta dt times r. R is a constant, so going to the next line, ds dt is the linear speed, the rate of change of distance traveled. D theta dt is the angular speed, which is denoted by omega. So I'm going to take that and I'm going to plug it in right here for velocity. So I have k equals 1/2 m times omega r, quantity squared. And then I'm going to rearrange some of these terms. So I have 1/2 times the quantity mr squared times omega squared. Okay? Now, if you recall, when we discussed rotational inertia, the formula for rotational inertia for discrete masses is the sum of mr squared. So I can see mr squared is here, mr squared is there. So this is actually the rotational inertia of that mass. So I could write it as 1/2 I omega squared. Okay? So this is the rotational kinetic energy of a single mass, which is not terribly useful. If you had a single mass, you would probably just use 1/2 mv squared. But what if we have a rigid body? Okay, so you have a rigid body. Here's the rigid body. It's got a pivot point there. And so it's rotating about the pivot point like that. So what we would do, if we wanted to calculate what is the rotational kinetic energy of this entire blob, what we would do is we would imagine dividing the blob up into a bunch of sections. Okay. All right. And then to calculate the total rotational kinetic energy, we would sum over the rotational kinetic energy of each of these individual sections. So it would be the sum of 1/2 I omega squared. And I'm going to put an index here, where the index is what differentiates between these different sections. So maybe section 1, section 2, section 3, section 4, etc. Okay? Now, an important point about rigid bodies is that all points on a rigid body have the same omega, the same angular velocity. That's a really important point, okay? Now, why is that? I can imagine if I have this calculator here, all right, and here's the pivot point, and I let it rotate, maybe do half a rotation. Every single point on this rigid body did half a rotation. And furthermore, every single point did that in the same amount of time. So the angular displacement was the same for every point, and the time elapsed was the same for every point. So that's the same angular velocity. Okay? So what that means is that this omega term is the same for every part of the sum. So I would just get so I can factor it out. So I get 1/2 times the sum of the rotational inertias times omega squared. All right? Now the sum of these individual rotational inertias is just the rotational inertia of the entire thing. So we get the same formula. 1/2 I omega squared is the rotational kinetic energy of a rigid body. Okay? Correct. The actual distance traveled depends on r. Yeah, so that's a good point. So if I have like a baseball bat right here, and I move the baseball bat in a half circle, the end of the baseball bat goes in a circle that is very large, right? This big arc, the end of the baseball bat goes. But if I look at a different point on the baseball bat, for example, right here, and I go, it only moves in that small arc. So both of the points, both the end of the bat and this point, underwent a half circle in the same amount of time, but this little one did a small half circle and the big half circle. So the linear speed of the end of the bat is greater here, but the angular speed is the same for every point. Okay? Linear speed is not the same, but angular speed is the same. Okay, so when rolling, when something is rolling, things have both translational and rotational kinetic energy. You got both of them, okay? Why? Because when a thing is rolling, it's spinning, and it's also moving from point A to point B, okay? And so the total kinetic energy is just going to be the sum of the translational kinetic energy and the rotational kinetic energy. Okay? Now the formula for translational kinetic energy is just the same old kinetic energy formula. It's 1/2 mv squared. And the rotational kinetic energy is 1/2 I omega squared. Okay? Now, because this thing is rolling, as we discussed in the previous lesson, rolling implies that V equals omega R. So I can actually substitute in for omega. I'm gonna write omega is equal to V over R, and I'm gonna plug that in right there. Okay. So I get 1/2 mv squared plus 1/2 I times v over r quantity squared. So simplifying this, and I'm also going to multiply by m and divide by m on that second term, which I can do because that's equivalent to multiplying by 1. So in this second term, I get 1/2 mv squared times the quantity I over mr squared, like that. So now I notice that both terms have 1/2 mv squared, so I can collect them, and I get that the total kinetic energy when rolling is going to be 1/2 mv squared times the quantity 1 plus I over mr squared. All right, so notice how this is an important equation, and there's this extra term present, and the reason that extra term is there is because of the rolling. So there's an additional term that we didn't have if something is just translating. Okay. So how can we use this equation? Well, it's really useful in conservation of energy problems. All right. So what if we have, just a little example. What if we have an object that is rolling and it rolls down a hill? All right. So maybe the hill has a height y, and here's the object rolling, and it's rolling with a translational speed v initial. All right. It rolls down the hill, and once it gets to the bottom, we have another speed, a new speed, because it's going to accelerate as it rolls down the hill, which is v final. Okay. Hang on a second. I'm going to turn the heat off. Okay, so we could actually calculate the final speed fairly easily. We would use initial energy equals final energy. Okay. The initial energy consists of rolling kinetic energy and gravitational potential energy. So we have rolling kinetic energy. Okay. Notice how I'm using the initial speed. And then we have gravitational potential energy. Afterwards, after we get to the bottom of the hill, we don't have gravitational potential energy anymore. We just have kinetic energy. All right. Like that. So you can use this equation to solve for the final. I'm not going to actually plug in numbers. It would just be a waste of time. One of the things I wanted to point out is that I over mr squared looks kind of complicated, but it's actually really simple. So for example, if you have a solid sphere, the rotational inertia of a solid sphere is 2/5 mr squared. All right. So if I divide both sides by mr squared, I get I over mr squared is equal to 2/5. So my point is that this 1 plus I over mr squared, the I over mr squared is always going to be a simple fraction. And then when you do 1 plus I over mr squared, you get something So, for example, 1 plus I over mr squared is going to be 1 plus 2/5, which is 7/5. All right, which we can then plug into there. So this extra term just ends up being a multiplier to the kinetic energy. All right, so that's the first topic for today's lesson. The second topic is about what if you have a really steep ramp. And something is going to roll down the ramp, okay? So maybe you have something that looks like this. It's super steep, okay? Here's the thing. It's going to roll down, okay? Here's the thing. It might not actually roll, all right? And here's the reason why. The normal force, because the ramp is so steep, the normal force will be small. Okay, the normal force is going to be small. And because the normal force is small, the maximum static friction, which is equal to mu sub s times normal, will be small. Okay, now if you recall, when an object is rolling, the force that actually makes the object start to roll is static friction. Okay, so this static friction may not be enough. There may not be enough friction for the object to roll without slipping. So it might slip. Okay? So our goal is to sort of calculate what's going to happen in that case. All right? And so what you want to do is you want to treat this like any other rolling problem. But set the static friction equal to the maximum static friction, which is mu normal. Okay? So when in the last lesson I said, okay, static friction, just leave it as a variable, F sub s. And it comes out of, you can solve for F sub s by solving the system of equations. But here we have static friction is maximized. So we actually plug in for the formula for static friction. Okay. So let me review an object rolling down a hill. So if this is your hill, all right, and here's the object rolling, you have a number of forces on the object. You have the weight force that acts straight down. You have the normal force, which acts perpendicular to the incline, and it acts right there. And then you have static friction, which acts parallel to the incline. Okay, so when I do this problem, I'm going to choose the x-axis to be down the incline and the y-axis to be perpendicular to the incline. So my free body diagram is going to look like this: static friction, normal force, weight force, mg. And then when we learned about these types of problems, inclined plane problems, we were able to show with geometry that if this is the angle the incline makes with the horizontal, then this angle will also be theta. Okay. So then I can take this force, the weight force, and break it up into components. This would be mg cosine. This would be mg sine. So I'm going to write this force as two forces, which is okay to do. So I have, again, I have static friction going this way. I have normal force going this way. And then the weight force becomes mg cosine theta and mg sine theta. Okay. Now, the normal force has to balance out with the mg cosine theta. Why? If the normal force was bigger than mg cosine theta, the object would jump off the incline, or if mg cosine theta was bigger than the normal force, it would crush into the incline. All right? So the only sensible option is that normal force is mg cosine theta. And we went over this when we were talking about inclined planes. Once we know the normal force, we can calculate the maximum static friction. And it is equal to mu sub s times normal. But for normal, I'm going to type in mg cosine of theta. All right? So that means that the torque due to friction is going to be force times distance from the center. So I multiply this by r, and I would get mu sub s mg times r cosine of theta. So that's the torque due to friction. So now I go to my three equations. The first equation is the linear motion equation. Net force in the x direction equals ma. Oops, ma, not mg, but ma. And so the x direction is this direction right here. The force in the positive x direction is mg sine theta. The force in the negative x direction is static friction, maximum static friction. So mu sub s times mg cosine of theta. And that has to equal ma. All right? So that's our first equation. Our second equation was the equation expressing rotational motion. So net torque equals I alpha. As I mentioned in the last lesson, weight force doesn't exert a torque because it has r equals 0. Normal force doesn't have a torque because it is parallel to the line connecting the center to where the force is applied. So the only torque we have is static friction, which is mu sub s mgr cosine of theta. And so that equals I alpha. And then lastly, we have the equation expressing the fact that the object is rolling. Okay? So we're going to take this equation. Now in this case, when we did the problem before, we had our unknowns were friction. So before, the unknowns were linear acceleration, angular acceleration, and static friction. But now our unknowns are linear acceleration, angular acceleration, and the angle of the incline. Okay? So we're going to try to solve for the angle of the incline. So let me rewrite the equations on the next page. By the way, you can see that mass is in all three terms here, so mass will cancel out. So taking this equation, I can just really easily rewrite it as alpha equals linear acceleration over r. And I can plug that in right here. So that says that mu sub s m g r cosine of theta equals I over r times a. I can take this and solve for the linear acceleration. So I multiply both sides by r, I divide both sides by I, and I get that linear acceleration is equal to mu sub s times g times mr squared over I times cosine of theta. All right, like that. I can then take this equation for the linear acceleration and plug it into here. So now I have g sine of theta minus mu sub s g cosine of theta equals mu sub s g mr squared over I cosine of theta. So now I notice that all three terms have gravity, so gravity cancels out. All right, so rewriting the equation again, sine of theta minus mu sub s cosine of theta equals mu sub s mr squared over I cosine of theta. I'm trying to solve for the angle, I'm trying to get a tangent, so I can do an inverse tangent. So I'm going to add this cosine theta term over to the other side. Sine of theta equals mu sub s times the quantity 1 plus mr squared over I cosine of theta. So I added the cosine theta term over and collected like terms. Divide both sides by cosine of theta. I get tangent of theta equals mu sub s times the quantity 1 plus mr squared over I. And then I'm trying to solve for the angle, so I do an inverse tangent. And what I get, I'm going to put a star here because it's a special angle. I get that that special angle is inverse tangent of the quantity mu sub s times 1 plus mr squared over I. Okay? So what does this mean? We just solved for the angle. This is the angle at which where static friction is maxed out. Okay? So if the angle is greater than this special angle, the object will not be able to roll without slipping. Okay? So I'm going to have you solve problems like that on today's quiz. All right? This type of analysis is not always limited to inclined planes, rolling down an inclined plane. If you have something that is on a flat surface, and let's say you're pulling it with some applied force, if the applied force is too large, the object will slip. It cannot roll because the acceleration is too great and static friction can't make the wheel rotate fast enough. Okay? So I can't remember in the homework if I had you do a problem like this or a problem like this. But this is the basic idea. All right, so that's my lesson for today, and I will see you in the Zoom room.